Welcome everyone to another session on the PFC boost rectifier. And today's discussion we will do on the small signal analysis and the controller design of the PFC boost rectifier. And today's discussion, we would like to keep it simple and short. And in this course structure, we are here in the seventh week where we are talking about the single-phased PFC boost rectifier. And in today's discussion, we are going to basically look into the control of the boost PFC converter. Um, Two control techniques we will cover. Uh, and then we will talk about the small signal analysis of the converter, controller design, and a brief discussion on the simulation. So let us, we have already covered in the previous lecture about the operation of this converter, where we have seen there is one diode bridge rectifier at the front and a boost converter at the second stage. And now we are talking about how to control the current or how to control this converter. So basically, we are interested in controlling this inductor current IL, which sometimes we also say instead of IL, we in this lecture, we will also say IG. And we will use this to currents interchangeably because IG is nothing but the current which is flowing through the output of the diode bridge rectifier, which ultimately will get reflected as IAC, the AC current, the AC current drawn from the AC source. So therefore, we will, if we control IL or IG in a nice sinusoidal fashion, we will be able to control the AC source current nicely. Also, we must keep in mind that we have to keep this voltage V or V output voltage. That voltage has to be also kept constant. Okay. For example, for a telecom power supply, as we said, we need to have like a 48 volt at the output. Now, there are many control techniques which are available, and one of the most popular technique is this average current control, which we will discuss next. But there are other techniques like hysteresis, current control, etc. And these are quite popular and easily achievable. Okay. Now, let us see what this average current control uh, looks like. Okay, so in this technique, basically the inductor current or IGT, this is the IGT or the IL, whatever you can. So this is controlled. So basically, we are controlling this current, and what is the aim or what is our target? The target is that, of course, we are trying to follow the input rectified voltage, but the target for IGT must be that it must have a proper magnitude so that correct power is delivered to the load, right? For example, if I want to deliver 1000 watt, I must have the correct magnitude of the current which is flowing through IG, therefore it is flowing through IAC from the 230 volt AC grid. Okay, so a proper magnitude of current needs to be uh, established by the closed loop control. So this is number one. Number two is that this current should be sinusoidal in shape. Okay, because our voltage is sinusoidal. And so if it is sinusoidal, then our THD will be low. Okay. So that is the second requirement. As far as possible, we should make the waveform to be sinusoidal. And third point is it should be at unity power factor. Okay. Because usually these kind of rectifiers operate close to unity power factor, like 0.98 or 0.99 power factor. Okay, so therefore we have these three requirements from the source side. Of course, there is one more requirement, and I think that the load voltage should be maintained. Okay, load voltage is to be maintained. Okay, so uh, with these requirements, we will see how we can do this average current control. Now, in this average current control, so as I told you, first we need to get the unity power factor and the sinusoidal shape. Okay, so how do we get that? So in order to get that, we actually sense the VGT itself. Okay, what is VGT? VGT is this voltage here. Okay, the rectified grid voltage. Okay, the VGT voltage after diode grid rectified is this voltage. We can sense that voltage itself, which will become the reference for the controller, VRT. Okay, there is also a multiplying factor here, and I will talk about this multiplying factor sometime later. Okay, but you can understand that if we set VG as the reference to the controller, therefore VRT, this will also become something like this. Okay, and thereby we do not have to do any additional frequency determination or shape determination for the current. Okay, because VGT itself tells me that the frequency, whether it is 50 hertz or 60 hertz, and what is the shape. Okay, because the grid is already, VGT is already rectified sine wave. So therefore the by this VRT, if this VRT is properly, so if this VRT has the proper reference, then the current will follow. Okay. Now, in order to make this closed loop system, we must have a feedback of the current. Okay, this feedback comes from here. Okay, and then this current, it can pass through a gain. Okay, it can be sensed by a current sensor, and then this voltage here is the uh, voltage proportional to the current. Okay, and this is part of the feedback system, right? So we have this VRT and we have the VAT as the feedback. So we have got the reference and we have got the feedback. And therefore, this can be, the error in the voltage can be fed to the controller. Now, one thing that you can also, many commercial manufacturers, what they do is sometimes they use an op amp here. So this resistance, there is a resistance here, very small series resistance. They use that one. Okay, and then they actually get this voltage and put it into an op amp and get a corresponding voltage out of it. Okay, differential op amp. So here it is saying sometimes a differential op amp is used along with a series sense resistor to get an equivalent feedback voltage. So when the current flows through this small series sense resistor, then a corresponding voltage will be produced, and that voltage is proportional to the current that is flowing. And so that can be part of this feedback system instead of the current. That is also used. Okay. So anyway, once we have got the reference voltage and the feedback voltage, right, then we can get this error voltage, which is basically the plus the subtraction of these two, and then it is fed to a controller, PI controller, which will generate the PWM pulses and which will give the duty cycle for the switches. Okay. Now, if we have a good, very well tuned controller, then this V error will be 0 and therefore VR and VA will be accurately tracked. Okay. Now, so this helps us. So now we have got how to, so we do not have to do some extra things for getting the shape of the current or the frequency of the current, because as I told you in the previous slide, VRT takes care of the whole thing. Now comes the point, how do you get this V controller? So how do we get this part here? Okay, how to get this one? Because we remember we have to also know the magnitude of the current to be controlled. Okay, and V control sets this magnitude. So this V control here, this thing V control, it sets this magnitude of the IGT. It will set this one. Okay, the shape is set by VG, but the magnitude will be set by V control. How does it do that? Basically, um, remember we have talked this previously also, and that is that the we have previously talked in three-phase voltage source converter. The DC link voltage is actually having an information of how much is the power flowing, right? So because if you remember, if you can recall, if you are taking more power from the output, then the DC bus will fall. If you take less power from the output, then the DC bus voltage will increase. So therefore, the DC bus voltage at the output actually has an information of how much is the power being supplied to the load. So in this case, what we can do, so this actually can be an information of how much current we can actually draw. Okay, so when the DC bus voltage falls, we need to have more input power, and hence this Ig should increase. For example, if you see this Ig here, this is the Ig waveform, right? This is, if the power is drawn more, then the value of Ig should increase. Okay, when the power is more, and vice versa. So this is more power, P more. Okay, so therefore, if I monitor this DC bus voltage, okay, and see that the DC bus voltage is falling or rising, then we can put it into a closed loop control system. You can see this is the DC bus voltage reference, and we have a feedback, and we put it into a GCV like this, and that will give me the V control. Okay, so if the DC bus is falling very rapidly, then it will increase, and therefore immediately automatically the current will increase at the input side. Okay, so and if the DC bus is falling, this means that we do not need to have an input from the source, and the current reference will also fall down. So therefore we can say that this V control, this signal indirectly tells me or gives me the information that whether the power drawn at the load side is more or less. Okay, so accordingly, the magnitude of the current, here you can see this VR here, we had this VG, this gives the shape of the current, and this gives the magnitude of the current. Okay, and together when you multiply, VRT is obtained, and that sets the control. Okay, so V control, VGT is multiplied by a constant V control whose value is dependent on the DC bus voltage variation. Right? So here we can see that there are two control loops, right? One control loop is coming from the inner current loop. So this is the inner current loop. Okay, this is the inner current loop here. And this is the outer current, outer voltage loop. The outer voltage loop is coming from the DC bus voltage reference and DC bus feedback. So now we can actually draw this whole thing in a slightly different fashion, which is more traditional, which we know. Okay, so here you can see I have redrawn the whole diagram. Okay, but in a slightly different fashion. Okay, but the same thing which we have just explained. Here you can see there is this V0. This is the output voltage reference. And so there are now two loops. You can see here, there are two loops. There is one outer loop. This is one outer loop, and there is one inner loop. Okay, the inner current loop and outer voltage loop. Okay, you can see it here. Now, what is this outer voltage loop? In the outer voltage loop, we have this DC bus voltage reference. Okay, and we have a feedback from the DC bus here and gives this error. The error is fed to the DC bus PI controller, and that is multiplied by the profile, VG profile, which we have just now discussed. So it is getting, so this gives the magnitude and VG profile is coming. That is what makes the current reference. Okay, because this is the current which should flow through the inductor or IG star or IL star. Okay, so this is the current reference. Now this is the current reference, and we also have a current feedback. Okay, this is the current feedback that gives the error and which will form this PI. Okay, the inner PI for the current loop. This is the saturated block, and we have discussed it before why the saturated block is used. And this creates the DT, the duty cycle. Okay. Now, in order to design these PI controllers, we must have the model of the plant. What is meant by model of the plant? Which means that basically we are trying to control the the model of the plant. Means there's a small signal model of the plant where we are trying to find out how the inductor current is affected by the small changes in the duty. Okay, so this is the small signal model of the inner current loop. So when you change the duty, the inductor current will change, right? And this we have to find out. We will investigate and find out what is this expression. That inductor current changes the output voltage. Okay, and we will also find out this expression. Okay, once you have these two expressions, these are the plant models. Okay, you have these expressions, then we can plug in the values and can then design the PI controllers. Okay, so we will come to that. This inner current loop and the outer current loop sometime later. Okay, but what is important here, which we always follow, is that the inner loop is much faster compared to the outer loop, at least 10 times faster. So the bandwidth of the inner loop can be kept at 1/10 of the switching frequency. Okay, so this loop here, this loop, this is the inner loop. Okay, this inner loop is much faster compared to the outer loop. Okay, and suppose the switching frequency is say 50 kilohertz. We can keep the bandwidth of this inner loop at say 5 kilohertz. Okay, 1/10 of the switching frequency, because we do not want to get the switching frequency harmonics to get amplified by this. So we have a we have a minus 20 dB decay, a single pole behavior of this plant transfer function or the loop gain. And there we will see that at the switching frequency, the gain is falling. I mean, after the zero crossover, it falls at minus 20 dB per decade. And so this inner loop, this is the gain should be very small at the switching frequency. Okay. On the other hand, the outer voltage loop is much slower. Okay. So this is the outer voltage loop. Okay. This is the outer voltage loop here. And that outer voltage loop, it's part of the plant model, and it is much slower. Okay. It is usually 1/10 of the double line frequency. So it can keep it between anything between 5 hertz to 10 hertz, something like that. Okay. So this is how now we have to derive the plant model that IL hat by D hat and V0 hat by VO hat by IL hat. Okay, these models have to be derived to tune the PI controllers. But before we do that, I want to uh, go a little bit into the other controls which are possible. For example, another control which is very frequently used is the hysteresis control. Okay, we'll come to this thing after a few slides. We'll come and discuss this thing. But before that, I want to discuss a little bit about the hysteresis control. Okay, so it is another control technique which is also very frequently used, especially for converters which are running in critical conduction mode. Okay, it is a very simple technique. And if you recall, we had seen that in CRCM or critical conduction mode, we had a situation where the current was actually going from 0 to 2 times the current, average current. Okay, so this is the average current here, and this is the peak current in the critical conduction mode. Okay, and the peak current was double the average current. This we had discussed in the last lecture, critical. Okay, so it is very simple to use, but results in variable switching frequency. What is done here is something like this. Okay, so you can see here what is, again, there is this feedback of the voltage, and there is also V control. But here, what happens, the inductor, the current through the inductor, or the current through the switch. Okay, so the current through the inductor is sensed and is, so this is the current, zero current IG detector. The current through the inductor is sensed, and it is found out when it is going to zero. Okay, when it is reaching zero, okay, then a latch is turned on. Okay, usually this is a digital controller many times, or you can make it also an analog control. But when the current is coming to zero, then you turn on this latch, and then Q equal to 1, and it will drive the MOSFET. Okay, when the inductor current falls and comes to zero, you turn on the MOSFET, and then the inductor current will start to rise. Okay, like this. Okay, now here, after a certain time, the current has to be stopped. Okay, so that it will again fall. So in order to do that, what it done is the switch current is also compared with a reference. Okay, so the switch current is, so there is this control unit is there, and we have these, like what I had discussed, there is a VG and there is a V control. Okay, and they are getting multiplied, and that is, that multiplied voltage is compared with the actual current. Okay, whenever that value is crossing, same like previously, whenever the value is crossing, then this reset of this, so the current is flowing, it is going up here, and whenever the current is crossing this value, then the reset of the latch happens, and then the switch is turned off, and then the current will fall. Okay, again, when the current goes to zero, then a zero current IG detector turns on the switch, the current will rise, it will hit this boundary, and then it will come back. Okay, like this. And this boundary is set by this VG here. Okay, you can see here the VG is setting up this boundary along with V control, right? So this, so there is no PI controller involved here. Okay, and so hysteresis controller is easier to implement. But the problem that we have mentioned here is that it has a variable switching frequency. That is what is the main problem. And so it creates a wide spectrum of noise. And so sometimes it is maybe a better idea to actually go with the average current control. Okay. Now, if you want to implement the average current control, what you need to understand is that we have to do a small signal analysis. Okay, the small signal analysis of the converter has to be carried out for the necessary converter transfer functions. Like we had said, there are two important transfer functions, IL hat by D hat, and uh, here in this IL hat by D hat and V0 hat by IL hat. Okay, so we have to find out what are these transfer functions. So in order to do that, we follow the exactly the same procedure, okay, which we followed in the three-phase voltage source converter. Okay, and it starts with the steady state equations of the converter, and we cannot we cannot write it down again once more, but you can recall from the equations in the previous lecture. So what we have said here in the previous lecture, we had two switching states, 1 and 3, and there were another two switching states, 2 and 4. So by these equations, what we can say here is this, these are the steady state, these are the governing equations. VL is equal to VG minus D dash V0, where D dash equal to 1 minus D. And so L di dt is Vg minus D dash V0. Okay, similarly, when you combine the switching states 2 and 4 from the previous one, this current IC, so this was the IL current. Okay, so this is the LDIDT and this is the IC current. IC equal to D dash times IL minus V0 by RL. And so IC equal to C dV0 by dt and D dash IL into V0. And these equations are coming from the previous lecture. You have to just go back to that. Okay. So again, the process is very similar. We add a small perturbation to the all the variables in and analyze the system response under that small signal variation, small signal. So here we any variable we assume that the perturbation is very small as compared to the DC value or the quiescent point. Okay, so therefore we write this equation with from the previous equation we got this one and we gave a small price. For example, IL we say that this is equal to I capital L plus IL hat. Okay, like that. So here, so then for DIL plus IL hat by dt, and we write it the equations exactly what we have done in the voltage source converter also. We write down these equations and then we collect the AC terms one by one. Okay, so we write the equations for the first one, equation 1 to equation 3, and then this one for the capacitor equation, inductors equation and capacitors equation, and then collect the first order terms. And when you collect this one, then you get this two equations. Okay, DIL hat by dt and like this way. We can write it in a state space matrix format. Okay, so IL hat and V0 hat, these are the two energy storing elements. So inductor current and capacitor voltage, which we have kept as the unknown variable x hat. So x dot. So x dot equal to ax plus bu plus cv. Okay, this is the format here. Okay, x dot equal to ax plus bu plus cv. So then you can find out what is x, like that, the unknown quantity. Okay, so you can find out the important transfer functions. So IL hat by D hat is an important transfer function, and V0 hat and IL hat. What is this? Because the inner current loop is like the inductor current changes when you change the duty ratio. So therefore, IL hat by D hat is that what controls the inner current loop. On the other hand, once you change IL hat, it will have an impact on the output capacitor voltage. So therefore, we are interested into V0 hat by IL hat. That is the outer voltage loop. So in this way, these two quantities are important for us because we have to build that control block diagram. Okay. So let us first see what will be IL hat by D hat. So in this one, when you find out IL hat by D hat, we assume that this VG hat is equal to 0. Okay, that is the effect of the input has to be neglected. Okay, so yeah, so therefore we can write it like this way, and then we can find out, just putting this equation, we will find out that uh, yeah, IL hat by D hat, when you do it like this way, you will come to this equation here. You have to do a Laplace transform of these equations. Okay, which again follows the same way which we have written in the voltage source converter, but you can find it out. You can do it yourself also. IL hat by D hat will come like this. We have to do the Laplace transform, which is not shown here. Okay. Again, similarly, we can also similarly find out V0 hat by IL hat, and this will be the equations. Okay, so let us now, therefore, we have got this and this parts in the diagram. Okay, we have got these two expressions, and if we know the values of L, C, RL, d dash, if we know all these values, then we can actually know what is the transfer function exactly between here and here. And now we can actually design the two PI controller, 2 PI, we can do the tuning of the PI controller. Okay, so in order to do the controller design, we consider, say, 1 kilowatt DBR plus boost PFC that converts 230 volt 50 hertz AC to 400 volt DC. So the switching frequency is 50 kilohertz, and it is desired that the maximum ripple in that inductor is 20%. The maximum ripple is 2% on the capacitor voltage. So how do you design the L and C, which we have seen again from previous lecture? I'll just do it once more. IL max we can find out corresponding to the maximum power, okay, and the voltage. Here the voltage is 230 volt fixed, so 1000 watt and 230 volt, and root 2 is the because of the peak value. So this will come out to be 6.15, and we can design the value of L. Okay, this equation comes from previous lecture, and so the value of L comes out to be roughly 1 millihenry. Similarly, the maximum ripple in the output voltage is restricted to 2% for the capacitor. This equation we found out in the last class. We put it the values and we found out that the C is like this. So now when we have got the values, then the Bode plot of the IL hat by D hat is now shown. And we have earlier also said that to make the steady state error 0, what we need is that, so we see here that the the gain at DC is not very high. Okay, we have to make the gain very high at DC because we want to make the steady state error 0. Okay, so therefore what we can do here is that we have to put a pole at the origin. Okay, so when we put the pole at the origin, this after putting the pole at the origin, the loop gain is the orange curve, this orange line here. This becomes the loop gain. Okay, and it you can see the gain is increasing, right? The gain is increasing. The gain is increasing at DC, that we can see. But one problem when you put this as the gain, the phase plot, okay, if you look into the phase plot, it is reaching minus 180 degree. It is reaching minus 180 degree around 100 hertz here. Okay, so the bandwidth has to be lower than this. Okay, because we want a 40 degree at least phase margin, the bandwidth has to be lower. So we have to again tweak this plot. So one tweaking we have done, we have made the, by putting a pole at origin, we have increased the gain at DC. That thing we have done, but now we will tweak with the phase plot. Okay, so to improve this phase, what we will do is we will add a 0. Okay. Now, if you place a 0, the 0 will raise the phase of the system by 90 degree. You can see here now the phase plot has it goes to minus 90 degree, right? So it has shifted up. Okay. The placement of the raises the phase of the system by 90 degree. But now what we want is that the placement of the 0, so we always want that the placement of 0 should be such that the phase never dips below minus 35 degree. That means we have about 45 degree phase margin. Okay. And so we have placed a 0 around 100 hertz, right? And therefore we have shifted the plot up. But now we need the adequate bandwidth, because here the bandwidth was actually very high. Okay, this is like how much? It is very high. It is 70 or 80 kilohertz. The problem is that with the switching frequency of 50 kilohertz and with a bandwidth of 70 or 80 kilohertz, the problem is that the switching frequency harmonics will also get amplified. Okay, so we have to push down the loop gain. Okay, you can see here we are now pushing down. This is the loop gain plot. Okay, earlier it was 70 or 80 kilohertz, but now we are reducing it. We are reducing it to somewhere here. Okay, and then this will be so this will be about 6-7 hertz. Okay, so sorry, yeah, 6-7 kilohertz here. Okay, this is the 5 kilohertz. Okay, okay, so we are reducing it because remember our switching frequency is here 50 kilohertz. Okay, we want an adequate gain attenuation for the switching frequency harmonics. Okay, so we have kept the bandwidth close to like 5 kilohertz. Okay, and this we have done by pushing the plot downwards. Okay, so the plot in the previous slide had to be shifted down by 22 dB. Okay, so therefore an outside gain of 0.077 is added. This gain actually shifts the plot up or down. So therefore, this is the gain 0.007, and we have put a 0 at 200 at 100 hertz, and we have put a pole at origin. And so this is the format of the Kp plus Ki, which we know already. It's a standard structure of a PI controller. Okay, so you can understand that by putting the zeros and poles and by adjusting the gain, okay, we can actually work or manipulate this loop gain plot and make it as per our specification, as per our requirement. Okay, so here in our requirement was the DC gain should be very high. This was one requirement. The other requirement was that 50 kilohertz, the switching frequency, the gain should be very small so that our crossover frequency will be, we have kept it around 5 kilohertz. And here also we see that if you operate in this region, the phase margin is at least, yeah, more than 40, 60 degree or 70 degree. That much of phase margin is present in the plot. Okay. So, yeah. Um, so therefore, in this one, the controller for the outer voltage loop can be designed similarly, and the entire transfer function of the inner current loop multiplied by the transfer function Vi becomes a plant function. So for the outer loop, basically the inner loop becomes the gain of the system, and therefore, yeah. So this is the total loop gain, and you can see here, this is the yeah, this is the 0 dB crossover frequency of the loop gain, and this is actually kept quite low, about 10 hertz. Okay, this is 10 hertz here. Okay, for the outer voltage loop. Okay, so yeah, this is how the overall transfer function looks. So now we will put it into some of the simulation results. Let us see how it happens. So the boost PFC rectifier is simulated in, we have simulated in MATLAB, and at t equal to 3 seconds, okay, there is a load change which occurs. So the initially voltage is set at 400 volts, okay, and at t equal to 3 seconds, we have a change of the power from 1 kilowatt to 800 watt. But you see there is a momentary voltage drop, okay, but it again comes back to the 400 volt system, okay. And again at t equal to 6 seconds, a change in the reference voltage is given from 400 to 450. Okay, here also 400 to 450 is given, but the actual voltage, okay, the reference voltage is the step input, but the actual voltage, which is the golden color or yellow color, that is following the output voltage. Okay. If you zoom in to this one, if you zoom in this portion or this portion here, you can see what is the voltage actually looks like. Okay, the voltage ripple can be seen, and it is equal to 8 volt. Okay, 2% of the output voltage as desired. Right. So this voltage here, 2% is the ripple here on this voltage. The converter duty ratio D is also shown, and this converter duty ratio, you can see it is varying between a minimum and a maximum value, as we have already understood previously. And these are some of the input voltage and the input current. Okay. So the input current for different loadings are shown. Okay. You can see that the input current is quite sinusoidal in nature. Okay. It is almost at unity power factor, right? Um, but one thing you can observe initially at lower loading, okay, so you can see this is 10, this is 10, and this is 20. So at initial lower power level, the input voltage has slightly more distortion as compared to the higher loading. Okay, this is expected. If you remember that we had said that at higher power, more of the regions come into under the purview of the CCM mode. And so, yeah, so therefore, at higher loading, which is closer to the rated loading, the current will become better and better. Okay, and the THD will become better. Okay. So if you carry out the harmonic analysis, which we have shown here, the THD of the input current is 3.8%, so which is acceptable, okay, as per IEEE standards, which is less than 5%, okay. And you can see here uh, the currents which are shown here, okay. If you zoom in on this current, you can see some of the lower frequency currents, and some of this current come from the lower frequency current. Some of them come from the from the second harmonic power variation. Okay, this is and another thing that we wanted to see is that the inductor current. Okay, this is the inductor current. Okay, the inductor current reference is this rectified sine wave. Okay, and the actual inductor current IL. Okay, it is nicely following this current. Okay, so the reference is tracked very well in this case, right? Where we can see that the controller, the inner current controller, is working very nicely. Okay. Yes, fine. So with this, we actually have come to the end of the Boost PFC. So if we summarize, we have learned in this part of the uh, course about Boost PFC operation, steady state operation, and how we have the DBR and the boost converter working together. And we also see how the inductors and the capacitors can be designed. We have taken an example previous class, and in this lecture we have seen how we can control the current. Two techniques we have briefly touched upon: average current control, which is quite popular. Both are quite popular. Even in fact, hysteresis current control is commercially available with some manufacturers in the form of some ICs. Hysteresis current control is very popular. But average current control gives better performance, and we have seen how to uh, model the system from the control perspective. And therefore, once we model the whole plant, then we can actually design the PI controllers, right? And the designing can be done using Bode plots, right? And we can actually tweak the Bode plot. We can shift it up, down, and we can change the bandwidth by adjusting the KP and KI values of the PI compensator. That's what we did through that example. We have also earlier seen a similar example when we were talking about three-phase voltage source converter. Now we have done it for also the Boost PFC. And we have shown some of the simulation results here. And the results are actually quite nice and as predicted by the theory. So with this, we conclude the lecture on Boost PFC. Thank you.